Good afternoon. Hope you had a good lunch. My name's MikeCarlson. I'm going to be talking to you today about some work that I did at home, and it concerns SOC performance. So when I finished my course at SAIT, I got on the job. First thing you find out is you have to use something like a search engine of some sort, usually associated with a SIEM. And in this particular case, I learned Splunk first. And of course, when I got home, I have a couple of servers that I bought secondhand from the ERA. And, I put a security onion install in there. And I wanted to get a little bit more familiar with how the actual SIEM really worked. So in the process of doing that, I eventually changed jobs and moved on to another company. I'm working at CDW at the moment, and we've got a new SIEM. And the SIEM works completely differently. So what I'm going to do is take those two things that I did, which is learning about how the SIEM works, as well as this SIEM works dramatically different, and I wanted to understand why it might or might not work. So searching is actually a pretty important part of technology for us. It's not something you study directly at SAIT. Searching made Google, and so it's not that straightforward and simple. I mean, Google's basically a technology company. The thing that made them successful was their web searches. One thing that many people don't realize is that most SIEMs that I've seen to date seem to be based on Apache's Lucene. Now, it has an Apache license that allows people to slice and dice it and take pieces out of it and use it, but it is actually, I'll show you a slide here in a moment and let you be the judge of as to whether or not those things are the same or not. So Lucene was written by a guy by the name of Doug Cutting, comes from just before 2000, 1999. He is got to be a fairly distinguished researcher because he started at Xerox PARC, which was probably notable because it was so many things came out of PARC. One of them is actually Windows, is something that was originally invented in PARC. But then he went on to work with Apple and then Excite. And then he joined Apache to work on their Jakarta family of search engines. So some of the things that you might recognize, Elasticsearch, which is a common open source, which will also be included in something like Security Onion, is based on the Lucene engine, and it was originally written in Java. So my recommendation is if you look through the book Elasticsearch, the Definitive Guide by Clinton Gormley and Zachary Tong, you can find out all the nuts and bolts of how the search engine underneath there actually works. So here's my comparison. The one on the top here, this is Security Onion, and this is the Elasticsearch. And then over on the right here, we have a picture that I nicked from the web that shows Splunk. So what are the key elements here that look the same? Well, for one thing, you can see the bar graph, right? And those bar graphs, they look suspiciously alike to me. I mean, if you have somebody draw two different pictures, I mean, usually they'll make the bars a little wider or different, have a different coloration scheme, but something will be different. And then underneath, you can see over on the left-hand side, we have this series of basically an index bar here. We have here one of our documents in here. You'll notice that there's a couple of columns in here, time is in here, and then you've got a JSON object in here. And these two look exactly the same. So, even if they have gone through considerable in-house adjustment, which I think is probably the case, the similarity is just, extremely high. So, the thing that you learn from this process, and I'll go through the little program here a little bit later because I have a simplified example, that was so different about the new SIEM that we got at work was that it indexes everything at search time. Now, most of you that work with the SIEM realize that the indexing is usually the first thing that occurs, and that heavy indexer is usually where the lion's share of the work takes place. In fact, as a general rule, the thing that limits the capacity of your SOC is actually your heavy indexer. So I have a picture here. This happens to be a picture I nicked from Logarithm, but it shows the general process in here. Over on the left-hand side, we have the agents. They send logs. Here's our heavy indexer. And what does it do? Well, it stores all the stuff that came across and creates an inverse index. The inverse index is what allows us to do the search. And then actually, ordinarily speaking, the AI engine and Logarithm is basically where all the rules are contained to determine detections that come from the seam. And then the platform manager is where you would input your searches. So this word index gets used and overused in the context of searching. We have an index, which is actually the place where we store the documents. And it has a structured format. And if you go back here, you'll remember that on the document on the right-hand side, you can see a JSON object. That's an index or a structured index. It contains all the information that's in the document. And that's an example of where we have something that people would call an index. And then we have index, which is kind of like a verb. When we actually do that process of creating that JSON object and putting them together in a collection, that's indexing, so it's a verb. And then very often people don't distinguish between the inverse index and the index. The inverse index is the part that goes through there, scrapes all the words out of the document, puts them into a big dictionary, and then using some rules and things like that, you can come up with an indication of what is the most likely document you're looking for. So I have another example here. On the left-hand side, we have a source document, which is roughly in the syslog format. And then on the right-hand side, we have the structured document, which is now in JSON format. You can see there's a little bit right at the very beginning there. It says 01 of August, 2019. And then you can see the curly brackets. That's actually a little header that goes in front of the JSON object. The rest actually just runs right through there, and it has ordered pairs in a JSON format. Now, I've kind of twisted this diagram a little bit. Originally, the right-hand side was actually under the left-hand side. Very often when people index these documents, the last field in there is actually the raw syslog input. So there's actually a large number of indexes. And one thing I found moving from working at a company that had a unique Splunk install to working in a SOC, when we're in the SOC, we have an enormous number of clients. We might have 40, 50 clients. It's actually tough to remember them all because you got so many people with so many different types of equipment and installs. And they have all these different tenants. And then within each one of those tenants, we have firewalls, which is usually the largest component. We have AV, URLs. Sometimes that's usually part of the firewall logs. We have a spyware log. We have an event log, which would be a Windows event log. And then that's further split up if we have an EDR, say a syslog, and then a whole bunch of data that would relate to how the SIEM itself is operating. And then very often we might even have logs on a client that might be used by the network operations center that relate to network flows and things like that. And then one of the things I want to point out is I've shown this index as if there was one index specifically for, say, firewall threats, but that actually covers a considerable time period. So for typical SOC, they might keep the data for 100 days, which is a little bit over 3 months. And then, as you move along forward, I add a new day on the right-hand side of that diagram. Somebody has to take the stuff off the left-hand side. And that means you have to have some method of tracking in that index what's new, what's old, what data was put in there, and how you would get it. So there's actually a large amount of overhead associated with this index and maintaining it. So because there's so much work, this one is shamelessly stolen from Splunk. The thing that differentiates this one from the one before is you can see that we now have an index cluster. We've now clustered this so that we can get more decent parallel processing. The collection here hasn't really changed at all. When we get up to the top there, the search head, that's where you put in the commands to do the search. But what it does is it actually goes and collects the data from the reverse index in the indexing cluster, and uses the reverse index to find what you're looking for, and then reproduces the documents. So I kind of summarized this one on here. We're using JSON structures for search parameters. It's by no means the only way. The little example I give here a little bit later on actually uses XML. We have a structured data storage, so the actual, once we finish with that syslog, it gets stored in the JSON format, and then the reverse index itself, the key to it, and then once again we get to a little bit here where we use what's a device called a cluster, which I'll show you in a moment, to make it scalable so that we can use multiple threads and do more parallel processing. Now that mechanism that we use is usually called a shard. It also provides some redundancy, and God forbid our search crashes in the middle. It actually writes the first shard. When that's done, it writes the second shard. Then it goes back and says, okay, I've completed all of the writes on this thing. If the server goes down and either one of those writes, you still have a copy of it so that you don't lose your data. And then, of course, the software is fairly sophisticated. At that point in time, it starts sending all the information on the indexer side to a cache. And if you've set that up properly and have enough storage on there, you can go back and recover that data later. So there's a couple of other things that are required here as well. That's the failover and the redundancy, but you also have health checks. I have 2 copies of that index. Do they match up? Are they the same size? Do they have the same number of fields in them? And then I mentioned this a little bit earlier here. We revise the old versions and retire the old data. So we're always constantly adding things to that index and taking them off. So this is more or less reproduced from that book I recommended. And the idea here is that you can see we have 3 nodes. So this looks like the Splunk install where we have 3 different machines. You can see that the R and the P are 2 different shards. This is actually a user definable parameter that you can design when you're building your system. Splunk will come with an automatic default, but you can actually control this and pick the number of shards depending on your situation. So say we want to write something to the P1. Well, we write something to P1, and then P1 is actually not the master or the first shard in there. P0 is here. So this is our master index. If it's going to the P shard, which is determined by the order it came in and where it's from, it writes to this PO shard here first. After that, it goes to the P1 shard. Then it goes back and tells the master node that it's done that save, and then it can delete the stuff from the input stream. So that's not the only place that we need redundancy. We also have our reverse index, and in order to make things either simpler or more complicated, depending on how you want to look at it, those are called segments instead of shards, and the actual reverse index is split up into segments as well. So, or basically reverse index shards. And in here, we get data that comes in. It goes into that blue box at the bottom, the in-memory buffer. The in-memory buffer actually collects the latest data, and if we were to go and search the index, we start with the last one that's there, which would be on the left-hand side with that little plate of pancakes. They're intended to represent discs, platters. It goes to the second one, the third one, and then it picks up the in-memory buffer as the last part. And of course, what this allows us to do is to access data as soon as it's available. And when I say as soon as it's available, you need a second or 2 in order for the machinery to catch up. Now, what happens if it crashes? Well, now they added another mechanism in here, which is a transaction log. And transaction log allows you to keep track of what you've added and what you haven't added, and also provides a method if things crash, you can go back to your last known good and then use the transaction log to recreate what you had in there. So, getting back to my problem here, I've got a new search engine. It works completely differently. And usually the problem that you're faced here, if you're working in a company is you say, okay, salesman came in here, we got a small corral of them over there, says, hey, I've got this brand new shiny super duper sock. It works with this new seam, and you say, okay, it's basically show me. Why does this work where the other ones don't? And I think we know full well that the existing socks are actually working. So the limitation is usually our indexer at the front end. So I've just said, okay, what happens if we run our indexer for 365 days a year, 24 hours a day is 60 minutes. We end up with a little bit over 500,000 minutes in the year. So because of the maintenance and removal and health checks and updates, and the daily load isn't actually completely uniform, we know that around 8 o'clock it starts to pick up, maybe 7 o'clock, and then it usually drops off around 6, 7, or 8 o'clock, drops off to low levels. And actually, I haven't shown it in there, but, well, actually I have. See on the daily load, there's a little peak there about 1 or 2 o'clock in the morning. Nobody runs the utilities exactly at midnight. It's against religion. They usually run them at 1 or 2. And so that's that little peak. And then if we look at the week, same thing here. We have weekly load, over the weekend the loads are lower. So we have time at that time where we can schedule maintenance. And also, we don't have the indexer running full speed through during that time period because there's less ingestion. And you can see this, if you look at your ingestion rates, you can see this daily cycle. So I've taken a wild F guess. Scientific wild F guess at about 65%. So now let's take a look at what happens if we actually wanted to make that search in real time. So say I decide to search the last day. So I've got 24 times 60 minutes. But you may recall in that earlier diagram on a big sock, we have sometimes, 40, 50 clients in there. And in this particular case at hand, Devo, it's actually a cloud sock. So we have at least 40 tenants. Of the indexes, we're only looking at probably 1 in 15 at a time because we're not searching all of the indexes at a time. And in almost all searches, we're really only interested in about 10 fields usually, maybe 8 to 10. And that could be based on a small syslog has 75 entries, and the largest I've seen, which is on a XDR, is 232. So you actually get a huge amount of winnowing down there. So if I take that all into account, the amount of time that it's going to take me, and that I reduce the efficiency by 65% there to allow for the fact that it can run the full load at the time, I end up with about a 12.5-second time for the search. And of course, if you're a little bit clever, you can pop up the screen right away. That only takes a second or two. And then the last parts of the search actually occur in the background while you're looking at the first results that you see, and you're barely even aware that that's happening. Of course, my job at the moment, I do a lot of reports for clients that come out monthly. So a 30-day report is actually pretty common, and I'm basically tracking all the data that we need to make a nice, pretty graphic and report. So if I do that, take in a little bit more optimistic look at 50 tenants instead of 40, 1 out of 20 indexes, and I pick something in the middle between the 130, 140, which is regular, and the 210 fields. I end up with about 1.25 minutes in order to do a fairly large search. Once again, the screen pops up the results quickly, really early, and you wait for the other stuff to take place in the background. Typically, when I produce one of these reports, I actually use an API to pull it. And so, the APIs never come back instantly, and actually they're usually set up so that they go in little groups. It takes a minute or two, for a couple of minutes, for those things to run. So the big conclusion here is that actually running a search in real time is a distinct possibility. Now, there are some other implications to this, of course, as well. One of the things that sort of led to this situation is that people did the indexing up front because they were very concerned that they might miss something. And, 6 months down the road, even a month and a half down the road, you don't want to have to go back and reread all the logs, right? So the preferred path has always been in the past to index everything. However, this comes at a price in that it takes up an enormous amount of storage. And I mean, truth be told, a lot of those seam logs, which are look after, the machinery, anything that the NOC wanted, but that's not security related, actually constitutes a fair volume, and you just never use it. There is mathematically a very small chance you're going to use it. So what happens is, by not indexing these things beforehand, you end up with a temporary index, and at the end of the day, or maybe a couple of days later, you scratch it and the actual storage volume goes down considerably. So if we take a look, just going back up, how much storage, the raw log is on the left here, the finished log is on the right, and actually this stuff gets stacked on the bottom. I mean, the volume of text that's in here isn't that much less than what was in the original syslog. So really, when you get down to it, typically I would expect that my JSON formatted index document is going to be about twice as large as the original log that came in. Now, it could be that you don't have very much that you're looking for in there. Maybe it's only 10%. That's a realistic possibility. It could be that, the data structure you have pulls out a whole bunch of fields and you put in new subnames and things like that. But I think this is probably a good rule of thumb, to work with in most circumstances. Okay. How much time does it save us by having a smaller index? Do we get a linear reduction? Because that was an assumption that I made in that calculation that I showed. And there's this gentleman, I don't know how I found it exactly, but I was reading through this Elasticsearch book and found this reference on the web: build a full text search engine in 150 lines of Python code. I thought, I can do that. Just download it. And actually, you download it from GitHub, so you don't actually even have to code it. And I did a count, and the 150 lines was generous. It's actually 138. But what's 10 or 12 lines between friends? Downloaded it, put it on my computer. The GUID's website is really good. It has an explanation on the data preparation, the indexing. Tokenization is another word for, or another way of expressing the fact that you put these words into sort of keywords. You see that tokenization word a lot in the description of compilers. Then you'll see that they have a rule in there where they go in, they switch all the case to lowercase. They take out most of the punctuation, so the columns are commas. And then they take out the most common words. So the I, you, me's, whatever. Wikipedia, if you're looking through the Wikipedias, gets ripped out. And then they have a thing in there which is called an inverse document frequency. It looks at how many times that word shows up compared to how many times it shows up regularly in the English language and in other documents. And you get a ranking from that allows you to determine which is the most relevant. And I think that's a huge part of what made Google so successful. They also had a good ranking system. So the guys that put this together had a bit of a sense of humor. The example they wanted to talk about here, or that they picked out of what is about 6.7 gigabytes of information on Wikipedia, is, geez, wouldn't it be great if we had a flood of beer? And you're probably saying to me, Mike, what's the chance of that? Well, apparently they had these huge vats where they were building porter, and the things collapsed. And aside from knocking some people on the head, they also drowned in the beer. So, safe to say that this is a relatively rare occurrence, both in the Wikipedia and that. And, well, there we go. What was the fatalities here? If you look in the lower one there, you can see this is the result on the serve. I think they had 6 people that actually got killed in this, drowned in beer. So it's actually quite it's a nicely put together program. I've got an example there for the run.py, which is the central program in there. You can see that it downloads a couple of different let's see. Okay, it downloads the abstracts. This is a function that it creates. It's got some documentation in there. Tells you that it's going to download that XML dump. It's got an @timing function, which keeps track of how long it runs. And then if we get down to the bottom here, you can see in here that they've done a search for the London beer flood. And then they've also done, a search in which they do a ranking. Turns out the ranking doesn't make much difference in this case because there's only a couple of entries with a beer flood in it. So that's not really necessary. So then if you can download a copy of the presentation, you'll see that I've made a couple of little changes in there and identified little things. That's where the search index, where the actual search terms are included. I did some changes in here, which I'll outline shortly. The data is actually stored in a compressed format, and that's actually typical of the SIEM as well. The actual search engine, they'll store the data in a compressed format, so it takes up less room. And then the way the guy set it up originally, he was mostly concerned about how long the search took. Didn't actually show any results, so I put in a little, that's what you would need to add to it in order to actually see the results. And I talked a little bit earlier about the stemmer, the thing that takes out the common words, and you can see the B, T, of, A. One other thing it does in stemming is, it would look at stem as the root word. It takes the INGs off, it takes the S's off for plurals and things like that. And actually setting up your stemmer so that it works efficiently has a big impact on the performance of the search engine as well. And then I've got an example here where the structure is set up for the storage of the document. And then here I've got a picture of what the data actually looks like. It takes a few minutes to load because it's 6.7 gig and VI takes a little bit of time to load that up. But you can see that at the front there, it's got the doc statement. The end of the document is here with the /doc/doc. There's a whole series of sublinks in there, and this data is actually filled with a pile of garbage, might be the wrong word, but extraneous information would probably cover that. The meat of it's located not in the URL, but in the abstract and also in the title. And then I ran this thing here. Originally, the original search took about 800 seconds, 847 seconds. But of that, you can tell from the timing how much of it was the actual search being done running through that big dictionary, which is the reverse index, versus how much time is spent to build the reverse index. And the ratio is huge. It's 0.03% of the time is actually spent in the search, which means that it takes 3,200 odd times longer to actually create the index than to actually do the search. Now, this example might be fairly simple in that it's, it just got beer and flood in there, but it's the indexing, not the search, that actually takes all the time. So then what I did is I took that data set, the 6.7 gigabytes, took out every second document out. Then I took every fourth document out, and then I took every 10th document, or kept every 10th document, kept every fourth document. And what you find here is that the amount of time that it takes to do the search, which is on the left-hand side, is basically linear with the number of entries that you have in there. Now, those entries vary in size, and this thing works out basically on average. So the next thing I did is I said, okay, if I wanted to make the search even more efficient, if I happen to know the date that this beer flood was put into Wikipedia, I could maybe make that search even more focused. And so what I did is I split it about 20 pseudo years. I started in 2002 and went to 2022. So it's into 20 parts. And what I did then is I said, okay, I should have about the percent of the full data set time for indexing should be about 5%. And I just used a random distribution. I used a random number generator to decide which year it went in. So what this shows us is that, once again, if we split this up even further, we can get more efficiency by dividing where we search up into smaller bits. And it's also about roughly linear in terms of the efficiency increase. So I've shown a number of data set inputs here. I picked a couple of different examples off the web. Top one's a Fortinet. You can see that the style is a little different. They have blanks to separate the fields, equal signs with no spaces in order to put things in. And if they have a string in there that has any spaces in it or something like that, they use quotation marks. Palo Alto's is a little different. They don't show the fields at all. It does that in a numeric order. If there's nothing in there, you'll get a comma with nothing between them. And then Cisco uses a standard Cisco log format. They use a colon to divide their stuff up, and then they'll have the field space and then the actual value followed by a comma. And I also included checkpoint in there. Checkpoint's got a standard syslog as well as an internal format as well. And you can see that the way these things are split up actually varies quite a bit. The length, like I said, can vary from as little as 50 to over 230. So we talked about space implications, so I'll skip that. The next thing I did is I said, yeah, I have all this data in here that is really not used. So what happens if I strip this out? Now, this is also would make a case for making sure that your index doesn't include the raw string in the indexing process as well. Keep it as a separate file. And when I did that, I actually reduced the size of the files by, just a hair short of 75%, but it made only about a 15% difference in indexing time. And of course, if you think of that thing looking for words, the way sublink is set up, we build all these HTTP searches on the sublink in here so that they don't have any spaces in them. So it's not going to find any words in there, then be able to produce them to 5 characters or to something that can be stemmed. So it basically goes through all that. And my point here is that if you can remove the extraneous data, it's not nearly as important as the stuff that is actually fully indexed, but it reduces the amount of time by about 15% on average. So the whole point of my talk is this, and this is the reason why this search methodology works, is the key to this thing here is your success is measured by the amount of work that you don't actually do, whether it's indexing or in putting it into the original document format or reverse index. And that's not actually used. You only use, in most cases, a very small subset. So my summary is search indexing is the biggest part of the work. Break the search up into the smallest pieces you can. Eliminate any data that's not used. And then I think actually, this thing may not work for everybody. I gave an example in a scene where, there might be 40, 50 co-tenants. If I have a single install and I'm working in a company that has just a scheme, say Splunk logarithm, am I going to get that 1/50 or 1/50? No, I'm not going to get that. So it will actually be situationally dependent. And the other half of the situationally dependent is, if you've got a search where you've already eliminated at the syslog stage, or you've gone to the problem of trimming that down ahead of time, you may not get these huge increases in efficiency, but for the way most data that I've seen being prepared these days, it probably will. The other suggestion I have here is split indexes in the time dimension. And this is something else that the SEAM does, that it stores things in by month, by year, month, and day. And each one of those is a separate index. So instead of going through and taking that huge, massive index and going through there and working your way through and finding the old ones and taking them out, it just chops off the last index, adds the new one for the day. So I think there's been some clever planning in there. One other thing that I think is really important here is your sock parser is actually something that's really important. If you can not even parse the data that you don't use, you may get some inefficiencies. My experience has been that the parsers are actually often a bit of a hang-up. They may not be, if you have particular equipment or unusual logging being forward, there may not be a parser already built for you. Some searches are going to take longer. I think if you go in there and you say take a look at, say, 6 months or something like that, you might find that you end up with a long search, and there's an option sometimes to run that on the servers in the background. That's something you may want to run in the background. And the last thing here is the mini search engine, and even the one that I was talking about here on the seam, doesn't store the data permanently. And that actually reduces the amount of storage significantly, because it's basically a little bit over 50% jump to keep the original data plus actually have it indexed. So my objectives here is to understand the new approach. The advertising materials said, that it worked for large government agencies. Certainly what I've seen indicates it does work. Details always matter. And, there's lots of people using these SOC seam engines for even things like banking and things like that. So it may depend a lot on what your situation is. And then I think the last point would be, we had a talk just immediately before this. It was by one of the instructors at SAID. And he said, one of the things that's really important in security is that sort of hacker mentality and the need to find out how things work and use that information to maybe break things or to use it to your advantage. I'm going to suggest that this experimentation with this mini search engine will help you understand what you're doing, and it doesn't take a whole lot of time, and give it a go. Last thing, the book that I recommended there was the Elasticsearch, the Definitive Guide. So you can see what that looks like. You can find it on Amazon. I found that threat hunting with Elastic Stack to be really helpful as well. And then these are kind of a couple of classic works on setting up network monitoring. Baitlich is two of the books, and then the other one was Sanders and Smith. And that's pretty much everything I had to say. I also stuck in a couple of on the very last here, the last two Python modules in there that I made no changes in, but if you download a copy of this, you can see exactly what I did and would be able to reproduce it. And then finally, cooperate. Okay. Let me do this. This is what it'll look like when it's actually running. This is just a small data set. This is just 5% of it. Takes about a minute. Might be a little slower than normal because it's got other things running in the background. There we go. The actual indexing time for is 65 seconds. It's a little over a minute, and it did 319,000 documents. And that's the end of my presentation. Does anybody have any questions? Fire away.
How do you avoid redundancy in your index? Say when you're ingesting this data, how do you avoid having the same keyword over and over in your index?
Actually, if you run that thing with a different data set and pick a different word, it probably does do that. But then what happens is it goes in there and it does the ranking. So then it says, okay, you've got, say you were using the word endpoint. This document's got endpoint in it, and it shows up as every 10th word or 11th word, and then this one, it shows up as every 40 or 50th word. It'll pick the one at the front. So it doesn't not get those, it just orders them so that you can hopefully minimize the amount of time you spend on doing that. There are no other questions.
A lot of thoughts.
Yeah, it's actually pretty. It's not like a 30-second wonder, right? It just takes a little while to get through it. The details of the process that it goes through and updating those documents, and then checking the efficiency and all that. And, the decision that you as a security analyst would make if you're running a seed, you need to decide on how many shards or seeds you need, and decide how much input volume you need. Sizing is important as well.
Showed up there the parts and getting companies like Cisco and Checkpoint, other ones. Could be obviously tailoring to specifically certain quantities and answers.
I think it maybe would be the next area where we can do some significant optimization, but yeah. As well as being the touch point, and this is one of the things to look out for when you're going to see you actually have parsers for the hardware that you're going to be collecting. Yeah. And the documentation on that is really variable. Some of them are just fabulous. You go, oh, here's a summary. Oh, that's a remit. Oh, look, an example. And what other that I can think of is, okay, they've got a separate document for every variation of their equipment they have. There's no summary here at all. You get into it and it's line by line by line by line. There's no example or anything else like that. So documentation is always very specific. Yeah.
Do you have major vendors that are on like index optimization tools that you have to have, or have you seen that?
Have not yet. There's some default parsers. I've seen some of them. But they've sort of indicated to me that if you spend the time to do it yourself and write the code, it will work more efficiently. Maybe you should buy a service hours.
So I know it's like I can't get these now. I'm not there for a while.
Not that I can think of, no. Actually, that would be actually good. All right. Thanks.